Remember? Like the first microscope is optical microscope. The second one is scanning electron microscope. And the third one is transmission electron microscope. Right? For optical microscope, what do you have? You have some kind of like the material, the equipment that is quite easy and simple, right, to operate. And what's happening is, and what's happening is that it's quite simple and easy to operate. And the way that you need to prepare the sample, actually it's not that hard, alright? But you need to prepare 3 steps. Remember what they are. First is grinding. Second is what? Polishing. And the third is etching. Alright? So you can see the grains in optical microscope. But for a scanning electron microscope, what's happening is like, อันนี้ครูสอนแล้วใช่ไหมลูกสอนแล้วเนาะ And for scanning electron microscope, what's happening is you have the electron beam, and then the electron beam interact with your sample, and then there are a lot of signals coming out, and you get a detector, all right? And the detector that you have, what's happening is the simple detector can give you the picture, right? The picture like that look like more like the 3-dimensional pictures. Alright, and then if you are rich, you can get like some kind of another detector that can detect X-ray. And when you have X-ray that you detect, what's happening is you can know the composition, right? You can know what material it is, okay? And then for the final one that we just mentioned last time, it was transmission electron microscope. For the transmission electron microscope, remember? Sample, and then electron must transmit through it. What's happening is the sample must be very thin. Alright? So what's happening is like we need to make the sample very thin. But what good about transmission electron microscope is it can have like the magnification of 1,000,000. So that you can see arrangement of the atoms. Okay, so this is what's happening, okay? And also, if you want to use TM, you can also use it at lower magnification, and you can see the dislocation and semi-crystalline structure of polymer. พี่ใครทันบ้างลูกทันไหมใครไม่ทันยกมือใครทันยกมือ Okay. Alright, so now what's happening is we just continue with the new one, right? This is a new content for today, right? So after we talk about the microscope, so you know what? When you have like optical microscope, it's easy. You have the sample right here, and then just use the light as a medium, and you can see it. Right? But for electron microscope, both SEM and TM, you need to put it into the chamber, and you need to vacuum it out. Right? So it's quite hard to operate a little bit. And then what's happening is there is another kind of things that can make you see the sample, especially on the surface of the sample. They are called scanning probe microscopy. What's happening is, look at the word. The word is probe. Probe is something like that. Scanning probe microscope. What's happening is you have the probe, okay, and then you scan the probe throughout your material, and there will be some kind of signal, and that can be interpreted as a picture. All right? Okay, one more time. So scanning probe microscope is just that, like you have the probe, and you just like move through the surface of the sample, and there will be some kind of signal coming out, and detector kind of detect it and interpret it, all right, as a picture. Okay, so there are quite a lot of scanning probe microscope. What's happening is we are not going to learn all of them. We're just going to learn only how many? Two of them. The first one is atomic force microscope, is AFM. Another one is scanning tunneling microscope, or STM. Alright? So what's happening right here is, if you take a look at here, look at this schematic picture. You see? probe, alright? หัวอ่าน right? You have the probe, and then this is the way that your sample look like. So all you do is just move through like your sample. See that? And then what's happening is like the picture would come out like that. See that? For example, here you have the graphene. You know what graphene is. We already discussed about it. And you have the probe and just go through the sample, and this is what it looked like. You see that? Alright? So let me ask you, if like the scanning scanning probe microscope can give you good resolution, high magnification, yes or no? High or low magnification? High. You see that graphene actually, this is quite small. It's like nanometer range. Okay? So this is the way it is. Just scan through it. And if like that is the bump, you see that? Just like it will come out like that. Right? And if you take a look at the picture, the picture that comes out and it looks pretty much like yellowish, orangish, like that. You can guess that they are like the scanning probe microscopes, right? So actually the first scanning probe microscope is atomic force microscope, right? Okay, what's happening is this is your sample and this is a probe and you scan through it, right? Actually, what's happened is, like, what do you think? You would imagine that the probe will be just like attached to your sample or just like touch your sample. But actually, if your probe kind of touch your sample, what's gonna happen? Your tip, you know what? The tip of the probe, actually, the size is just in nano range. The tip, if it just keep touching, your sample surface would be damaged. And the tip itself would be damaged too. The tip would get blunt, right? Actually, what happened is the tip of the probe and the sample, actually, it's just like not attached to it. There are just small space. You know what? Like in the range of like nanometer. And how can it does not touch and it can give the signal? Because you know what? At the tip of your sample and on the surface of your sample, you know, each of them consists of atoms. And atoms normally they have attraction or repulsion anyway. So it just like keep like the distance like that all the time while we can detect the signal. Okay. ฟังครูพูดทันไหมทันใช่ไหมคือก็อย่างที่บอกมันติดไม่ได้เพราะมันเดี๋ยวเดี้ยงนึกออกป่ะแต่ว่ามันห่างได้เพราะว่าท้ายสุดมันมีแรงกระทำโอเคป่ะ so that's why we call it atomic force microscope. You see that because like there are some kind of force between the atoms of what? Between the atoms at the tip of your probe and the surface, alright, of your sample. Okay, so this is called atomic force microscope, right? So if you take a look right here, you see these are the atoms of sodium chloride. You can see the atom. That's why I told you that it can give you high magnification. How about here? Here you can see like there's some kind of rough surface, and the range actually is just like micron size. See that? And actually the way that they do it, okay, right? This is your sample, okay, and this is the tip, okay? This is the tip of the probe, all right? And then what's happened is you have the laser and put it right here, okay? And then if like the sample is bumping up, right? This tip just bump up. And when the tip bump up, what does it mean? It's just that like the angle of laser will change. See? And actually the detector can interpret the change of like the angle that the laser comes as like the roughness of the surface. Okay, bye. Right? So in this case, what's happening? What are they? CDs and DVD. Actually, like when you just burn the CD, it look like that. That would be some kind of proof. When you just like cross through, have the scanning probe microscope like the FM, go across it, this is what you will see. Okay? Alright. So, and actually this one, the next slide, I don't have it. The next slide is STM. Alright? Scanning tunneling electron microscope. You will see that. Okay? For the FM, the principle is just that there will be some kind of interaction between the atoms, between the chip and your sample, right? But for this like scanning, tunneling electron microscope, if you see, you will see some kind of similar features, all right? But what is more exciting is that you see right here, okay? For the scanning, tunneling electron microscope, when it came out around 30 years ago, people are like very excited about that because you know what? Some of the scientists, okay, move the atoms. Okay, here, what you see, this arrays of those are atoms. Okay, some scientists at IBM, they move the atoms and take a picture by the scanning tunneling electron microscope. All right, and they move the atoms and it's like dot, 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 dot in the letter of I, B, and M. So people just like so excited about it because like it's just the atomic level, all right? So that they saw it for the first time. Okay, so let me ask you the question. Okay, so for scanning tunneling electron microscope, can you see small pictures? Yes, you can see in the range of atoms. See that? Okay, so that's pretty much about the equipment. Okay, so next. Okay, give yourself a round of applause. Why? Because we finished the structure of metal and what? Ceramics. Okay, so now what we are going to do next is polymer. Okay, so polymer is pretty much everywhere. So let's start with the word polymer. What are they from? Polymer. Poly plus monomer. So that means like there are a lot of monomer and they combine them, all right, into polymer. So what is the name of the reaction that causes the combination of monomers into polymer? Someone already answered it. Okay, let me ask this question one more time. Polymer are from poly of monomers, right? So that means there are lots of combination of monomers and reaction involved in combination of monomers. What is this reaction called? Polymerization. Okay, so that's pretty much it. Monomer and combine and we get the polymerization process and we get polymer. So, and for the bonding of polymer, I already taught you. Remember? In the chain, we think about it as mama, right? Right? As in standard dough. So, in the chain, what are the main bonding about that? We talk only, right now, we know only 4 bonds, right? Ionic covalent, and ionic covalent, and metallic, and also van der Waals, or hydrogen, right? So, in the bond, in the chain, C and C and C and H or whatever, within the chain. What kind of bonding? สอนแล้วจริงๆนะ covalent, right? Covalent. But between the chain, we have the van der Waals. That's why I told you that even though covalent is quite strong, normal polymer is not that strong because between the bond, quite a lot of time they have van der Waals. See that? Okay, so this is pretty much what I'm covering. And then next, what we are talking about the way to categorize polymer. Okay, one thing, what I'm talking sometimes is not actually the same, exactly the same as what you have in your slide, alright? Because what's happening is if you don't drop it, okay, right after midterm, not right after midterm, after midterm you will repeat this one. So right now, what I'm doing is just like talk about overview of polymer, which you will learn it one more time. Okay? So for polymer, we can categorize polymer according to first is some kind of source, second is some kind of application, and the third is some kind of like structure and property. So about source is so easy, synthetic and natural. So let me ask you, your cloth, okay, is it polymer? If it is cotton, it's polymer. So it's synthetic or natural. If it is pure cotton, it's natural. Your skin, the wool, actually natural. Alright? So basically, you know a lot about polymer, natural polymer. But for synthetic, it's quite easy for you, like polyethylene, polypropylene, poly whatever. See? This is the way that we categorize according to source. And then next, categorize according to the application. For application, we can use the polymer as the glue, right? Glue, as a wrap, the plastic wrap for your food, right? As like some kind of rubber. You see that? So these are some kind of the way that we categorize it, okay? And the third one, we will talk about it a little bit later on. But let us capture about what we actually, this thing we already learned previously, okay? What happened is, okay, polymer consists of hydrogen, carbon, right? Agree with me? And then like the backbone, all right, of carbon, okay? So basically, they have covalence, okay? We just discussed. And then like when you have like it looks like the chain, and it can be big change with like with the molecular weight like 1,000,000 grams per mole. See that? And also starting material is called monomer. And then when we put monomers together, we have the process called polymerization. You see that? This is what we already learned. Okay? So, in this case, as I told you, okay, the first thing about monomer, okay, the easy monomer that we have learned is ethylene, right? Ethylene is quite easy. Have you learned about ethylene before when you were in the 11th grade? A little bit. Please say a little bit. C2H4 is ethylene. Have you heard of it? No? So please, if you never heard of it, please try to see it right now. Okay, ethylene, monomer, C, 2 of the C's, and 4 of the H. And remember, normally C has how many legs? 4. Okay, so 1, 2, this one, so this is not connected, so that's why that must be double bond right here. Okay, so when we just like combine ethylene and ethylene, what happens is this chain just like connect to this chain, right? So what happens is right here, there is no second bond anymore. So we just like put them together like this. Okay? Here. แป๊บนึงนะคะครูไปเร็วกว่าของครั้งที่แล้วใช่ไหมทันไหมงั้นแบบนี้ดีกว่านะเพราะว่าถ้าจะไปช้าเดี๋ยวพวกหนูหลับโอเคป่ะอันนี้ขอเล่านิดนึงเพราะว่าที่ครูไปช้าเพราะว่าพูดตรงๆเลยนะสมัยก่อนตอนครูสอน IUP อ่ะเด็กฟังไม่รู้เรื่องแล้วครูต้องไปช้ามากเลยแล้วครูก็ไม่รู้ไงว่าอินพุตของหนูปีนี้เก่งกว่าปีที่แล้วเยอะหรือเปล่านึกออกป่ะเพราะฉะนั้นคือสิ่งที่ครูต้องทำคือแบบก็ต้องสอนแบบช้าๆไปก่อนนึกออกป่ะแล้วท้ายสุดมีคนมาบอกว่าหนูทานปุ๊บเราก็สามารถไปเร็วได้ดีกว่าไปเร็วทีเดียวโอเคป่ะเพราะฉะนั้นเอาตามนี้นะลูกโอเค Okay next เฮ้ย can polymer consist of every single element in the world? Not really, okay? The ones that are in polymer that we see normally are those kind of like yellowish thing right here, right? You have carbon, nitrogen, what else? Oxygen, chlorine, what else?
silicon, phosphorus, sulfur, and chlorine, and also don't forget hydrogen. You see that? Okay, so let's talk more about monomer. Remember, I told you that like some of you, even if you never heard of ethylene, I asked you to remember ethylene, right? Because ethylene is the most common one that we will learn is C2 and H4, 2 of carbon and 4 of hydrogen. Okay, so and you would hear about polyethylene quite a lot because it is used as like a common container, the plastic bag or even sometimes plastic bottle. All right. Has anyone heard of polyethylene? Yes or no? Yes. Who never heard of polyethylene? Raise a hand. Who heard of it? Raise a hand. Okay, so you see, so remember, ethylene monomer is C2H4. Okay, so in this case, you know about this, alright? Okay. เขาไม่ได้บอก หาไปก็ไม่เจอ Okay, so in this case, you see, C2H4 and then one of the H is replaced with choline. What do you call it? Vinyl chloride. Actually, if we talk about like polyvinyl chloride, you just like, what the heck? But if I talk about PVC pipe, you see that? P, poly, V, vinyl, C, choline. See? Polyvinyl chloride, PVC. See that? You see? It's so simple. It's just start from ethylene and replace this one H with Cl, PVC. See that? And then next, okay? When you learn about this, you learn about this long time ago. Alright? That you say that 1C is ethyl, 2C is 1C is methyl, 2C is ethyl, 3C is methyl, propyl, right? 4C is butyl. Okay, so in this case, if we replace H with CH3, so how many C are there? 1, 2, 3. So we call it propylene. See that? So basically, we start with ethylene, and then we just like replace one H with the CH3. So what we have is 3C. Right now we have propylene. See that? Easy. Next, if we just replace, you see, supposed to be all H, but we replace all of them to be F. Look at here. You would hate me at first, but don't hate me. Look here. Is tetra. Tetra means 4. Fluoro means fluorine. Alright? Ethylene is like that. So basically, tetra fluoro ethylene is just like ethylene with replacement of our H with the F, right? Fluorine. And you just like poly tetrafluoroethylene. You just like, I hate it. I don't care. Why do I need to remember? Well, actually, it's Teflon. Okay, Teflon, something to coat Korean king or whatever. It's Teflon. Teflon is what? Actually, is start with ethylene. Actually, not start with, but actually, it's so similar to ethylene. What happens is that F is all replace the H. That's it. You see that? Next, how about we start with ethylene and then remember the word benzene. You see that is like the ring of benzene. The ring of benzene is 6 of the C, right? With alternating double and single bond. See that? So when we replace one of the H with one benzene, we call it styrene. You know the word styrene? You don't care. But have you heard of the word styrofoam? It's a container where you eat. It's the foam. Alright? You see that? You may have heard of the styrofoam. Actually, it's a foam. Foam ใส่ข้าวอ่ะ Okay ป่ะ So and then in case if they come out like this, don't worry about it. That's too hard. If it's come out, just let it go. All right? Okay. Let me summarize it for you. Hanilo. Okay. Let me summarize it. You have monomers and then polymerization them, so you get polymers. All right, and for the monomer, each of the monomer and or polymer within the chain you have covalent bond, and then like between the chain normally you have like secondary bond like hydrogen bond or van der Waals bond. All right, so I talk about the monomer, and monomer I just like give you the example of just like ethylene. Ethylene is quite easy, and then ethylene consists of 2C and 4H. And then like one H is replaced by Cl, we have PVC. And one H is replaced by CH3, we have propylene. And if one H is replaced by benzene, we have styrene. And then like if all of the H replaced by F, we have it, Teflon. That's it? Okay? Here. Simple enough? Alright, simple. Right? So next, okay? What we have learned so far was like the techniques to characterize the structure of the material. Like for XRD, what do we have? We have like the machine, right? That like give you the X and Y axis, right? And then there's the P. X axis of XRD or X-ray diffraction, we have the angle, right? And Y axis, we have the intensity and we get the P, right? And those P can tell you like the structure, what material it is, and how the material is arranged. Those are the structure about about metal and ceramics. In this case, okay? In this case, if we want to know the structure of polymer, do we care a lot if the crystalline polymer is BCC or FCC? Sometimes we don't, okay? Right? So what we care is, you know what? What is bonded with what? Okay? Like for example, if C is bonded with C, that is one example. That is one property. You see that? If H, right here, H, C is bonded with H, one property. In this case, C is bonded with Cl, another property. If that is like C bonded with all of the F, another property. You see that? So what we care so much about that? About the structure of polymer is what? What's bonding? Alright? So in this case, for the structure of polymer, we would use the spectroscope to check it. And spectroscope, the principle of spectroscope is what? You have what? You have the material, the polymer. And then what happens is you irradiate, just shine the magnetic radiation. Electromagnetic radiation like what? Light. Light is considered electromagnetic radiation, right? IR, right? IR is what? Infrared. UV, you know UV, ultraviolet. And sometimes radio frequency or whatever. Okay, so those are electromagnetic, all right? And then when you shine those electromagnetic radiation onto your sample, what's going to happen? The bond is staying the same at certain frequency. The bond is changed, like for example, if the C is bonded with another C, and the electromagnetic radiation, for example, I am the infrared. Can you just hold, right? They are bonding. They are bonded. I just come and just like, oh. So what happening is the bond may be stretching. The bond may be like just rotating and whatever. You see that? So what's happening is, okay, people know that if we shine certain frequency onto the material, what happens is certain bond will be stretched or do whatever. And you know what? When the bond is stretching or whatever, energy is absorbed right? You know that? So what's happening is right here. There are a lot of ways of spectroscope. You can put like IR or whatever. You see that? So when you put into it, we call it IR spectroscope. And if you put like the UV, we call UV spectroscope or whatever. But in this case, we give the example of IR, infrared. Okay? So what happened is, look here. IR, does it have one frequency? Only one frequency, yes or no? No, a long range of frequency. So these are the range of frequency. Okay? So when you shine your sample, you shine the IR. Okay, actually IR is some kind of light. Can I call it light? So that you feel comfortable with it. Alright? So when you shine the light onto your sample, what happens is what? Okay? There will be certain transmission and certain absorption. Here. Do you know the relationship of between absorption and transmission? If the material can absorb light a lot, that means it would not transmit light. So it's kind of like reverse proportional. Okay? So in this case, in this graph, it gives you transmission. Alright? So first, when you shine the lights at this frequency, alright, there are a lot of transmission. And then at certain frequency, right here, what happened is transmission decrease. What does it mean? There are a lot of absorption. So when there is absorption, that means the bond right here is getting rotated or whatever. You see that? So we know that at this frequency, there must be some kind of bonding. You see that? So the sharp decrease of transmission means some kind of absorption that occur from bonding. So you know that there must be some kind of bonding right here. And here also, that is the drop, right? Drop of transmission, that means there's some kind of absorption. That means certain bond is doing something, absorbing some energy right here. How about here? You see that? Certain bond must absorb. See? Absorb certain energy right here. And here, certain bond absorb energy. Certain bond absorb energy. And here, somehow dropping. You see that? Certain bond absorb energy. So that means you will see that, okay, there might be somehow this bonding, this. And how the heck would you know what kind of bonding on each of the dropping of this? How do you know? Database again. You go and check and you see, okay, at a frequency of 400, alright? So, okay, then it's C and C bonding, right? And how about at here, okay, that is C and H bonding or whatever. You see that? อันนี้ครูมั่วๆนะลูกมันอาจจะไม่ใช่ C กับ C. Alright, you see that? So, let me summarize it for you. For the polymer, when we talk about seeing the structure of polymer, what we care is what is bonded with what. So what happens is we shine the IR or whatever onto your sample. And then if there is some kind of like drop in transmission, that means there is absorption that designate the bonding right there. And how would you know if what bond it is? You just like read the handbook. There that some kind of database telling you at this range of frequency is some kind of certain bonding. Okay? Simple or what? Simple, in principle it's simple, but actually it's quite hard itself when you do it. But like you just need to know only principle. Okay? So พี่จะฟังครูพูดทันใช่ไหมใครให้ครูพูดอีกรอบหนึ่งยกมือ ขอเป็นภาษาไทยได้ไหมเขาคงไม่ว่านะ sorry just like one more time in Thai sorry โอเคใจเย็นๆนะลูกไม่มีอะไรเลยค่ะ ก็คือเราเอาโพลิเมอร์ใส่เข้าไปโอเคป่ะแล้วคือมันมีโพลิเมอร์วางอยู่ปุ๊บเราก็ยิงแสงไปโอเคสมมติว่ามันเป็นแสงเนาะแสงมันมีหลายความถี่โอเคป่ะแล้วแสงเนี่ยที่ความถี่บางความถี่เท่านั้นที่บอลหรือพันธะอ่ะมันจะแอบสอบได้มันจะดูดแสงได้แล้วรู้หรือเปล่าว่าที่ความถี่ตรงนั้นน่ะหมายความว่าอะไรก็คือถ้าเกิดเมื่อไหร่ก็ตามที่มันเกิดการดูดกลืนของแสงเข้าไปชัดแล้วว่าแปลว่ามันต้องมีพันธะแน่ๆโอเคป่ะเข้าใจหลักการครูไหมหลักการคือแค่นี้แหละแปลว่าคือถ้าเกิดยิงแสงไปแล้วมันเกิดการดูดกลืนแปลว่าอะไรคะแปลว่าการส่องผ่านมันลดลงเพราะฉะนั้นสิ่งที่เราต้องการหาคืออะไรคะมันดรอปลงไปหรือออกปการส่องผ่านมันดรอปลงไปเพราะฉะนั้นเราก็รู้แล้วแหละว่าอ๋อเพราะฉะนั้นที่จุดนี้แหละเกิดการดูดกลืนของพลังงานแล้วไงคะแปลว่ามีพันธะแค่นั้นเองและอ๋อถามว่าจะดูตรงไหนใช่ป่ะประมาณส่วนมากเขาจะดูตรงนี้เขาจะดูตรงช่วงต้นโอเคป่ะโอเคไหมคะแล้วเสร็จแล้วคำถามคือแล้วไงแล้วเรารู้ได้ไงว่ามันคือพันธะอะไรแค่นั้นเลยไปดูในแฮนด์บุ๊กดูในคู่มือจบเลยเขาจะบอกเป็นเขาบอกมาเลยเขาบอกเลยบอกว่าที่400ที่400คือ C กับ C กำลังบิดกันอยู่ C กำลังดึงอยู่บอกชัดเจนมากโอเคป่ะคะเพราะนั้นทันมีลูกข้างหลังหนูทันแล้วนะโอเค so let's get back to our stuff alright so next do we need to carry on with this actually I have taught you already what is this crystalline and amorphous so in this case a lot of polymer are crystalline a lot are amorphous and a lot are semi-crystalline. Alright? So what happened is, as if I'm telling you, for the crystalline polymer, you see, the chain will fit into the structure, like, like if it is orthorhombic or whatever. But do we care in this case? Right now, like we don't need to go deep into detail, right, about this one. Have you seen these kind of things before? Have you heard of the word spherulite? Spherulite? What are they? What are they? They are the polymer that accumulate into sphere. Remember? I show you when we talk about the TM. See that? So spherulite is like it's a polymer consisting of the crystalline part and amorphous part. See that? I just show it to you one more time. Right? And in this case, again, if like the chain is arranged in order, we call it lamella and look like the instant noodle that we didn't boil yet. And then like you see that crystalline parts and then amorphous part, crystalline, amorphous, and when they accumulated with both crystalline and amorphous, we can get some kind of like spherical called spherulite. Okay, Hila. We talk about monomers, and we get a lot of monomers together. All right. What happened is, I'm asking you this question: does it need to be like for the monomer? Is it necessary that the polymer contains just only one kind of monomer? Yes or no? No. Okay. So one polymer can contain a few of monomers. Okay. So the polymer that contains only one kind of monomer, we call it homo. If you take a look at the word homosexual, that means people love the same sex. You see that? So when we talk about homopolymer, that means the polymer has only the same monomer. You see that? Okay. Same monomer, one kind of monomer, we call it homopolymer. And if we have more than one kind of polymer, we call it copolymer. Alright? So in this case, like in case if I have monomer A and monomer B, okay? Copolymer, right? We call it copolymer definitely because they have two kinds. Okay, so let's take a look at the arrangement of this kind of copolymer. If arrangement is like this, what do we call? A, B, A, B, A, B, A, B, A, B, A, B, A, B. Alternating polymer, right? If we have A, B, 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 A, B, 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 what do we call it? Block polymer. And then A, B, A, B, B, A, B, B, A, B, 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 A. What is it? Random. All right. So okay. So the next one. This is a little bit harder. So if we have the backbone, it's just one kind of monomer. And then we have the branch in another kind. What do we call it? Graph polymer. Okay, so this is like what we have. Okay, so next part. Okay, what we have is structure, molecular structure of polymer. Okay แป๊บหนึ่งนะลูก ใครเอาหิวเหรอ กินข้าวไปยังลูกจะส่งต่อไปข้างหลังได้ป่ะไม่ส่งไปตรงนั้นลูกในซึ่งมีสะอาดอ่ะแป๊บหนึ่งนะลูกเจ็บคอมาแล้วค่ะกินน้ำลงไปด้วยนะแบบสุดยอดมากอ่ะมันจะแบบลองดูกินน้ำต่อไปเลยแล้วก็แบบมันตื่นแน่
เย็นแล้วลมหายใจเลย
นี่เขาฉี่ตรงนี้หลอดลงใช้เขาลงไปข้างล่างโอเค ready เป็นไงสุดยอดนะกินน้ำต่อไปเว้ยแล้วจะตื่นทันทีเม็ดละ2 บาทนะจ๊ะที่รักพี่ ready let's continue we have an hour left เฮ้ยWhat we are trying to do, again, one more time, is that we try to get it finished as fast as we can, so that we don't need to call the makeup class anymore. Alright? So if today we finish like a lot we finish the whole chapter right here, and then a little bit of the next chapter. That means Saturday we can finish. We can finish the second and maybe the third chapter, and we are fine with it. So that means we can finish earlier, and then we can have the we can have revision, and then you don't need to come to class as soon as I finish the revision. You see that? All right. So, are you ready?
Yes.
Okay. So, hey. พร้อมยัง Okay, molecular structure. Right? Look here. If you have polymer can be the what? The linear. And in this case, it can be branch. Okay, think. If everything else is the same, linear polymer and branch polymer, which one would have higher density? Sure. When you want to pack it. Remember, packet. Something that is fold easily can have higher packing. So, I give you one more chance. Linear and branch, if other thing is the same, which one has higher density? Linear. You see that? Because linear can pack more efficiently. Alright? So, next, in this case, if we have like polymer, the chain of polymer, and then there is some kind of another chain to link those two chains together. We call it crosslink. And this crosslink, alright, we have like the whole chain crosslink. It's quite strong because you know what? These are covalent. See that? Normally I told you, if it is common polymer, covalent bond, but between the chain, if it is common polymer, it would be linked with van der Waals or hydrogen. But in this case, you have covalent bond, so it's quite strong. This one you will see a lot in rubber, okay, or elastomer, okay. Next, the first one. Okay. All right. Next one. You see here, polymer. See. You see? Have you seen this kind of network before? Yes. And normally network that we talk about, that we mentioned, is what? Is some kind of covalent. So in this case, the bonding is all covalent. Strong or not strong? Strong. So, okay. So in this case, we have linear. We have branch and linear. Tends to have higher density. And then we have the crosslink like this. We see a lot in rubber. And here we have what? We have network, which are covalently bonded. That means it's quite strong. Okay. So next, I told you that we can categorize polymer based on source, based on what? Based on application. And now we categorize it as structure. According to structure and property. Okay. So for the structure, we talk about three kinds of them. The first kind is thermoplastic. Second kind is thermoset, and the third kind is rubber elastomer. โอเคถูกป่ะแป๊บนึงนะลูกฟังนิดนึงครูรู้สึกว่ามีหลายคนกำลังดิสคัสกันอยู่ซึ่งมันดีโอเคป่ะเพราะฉะนั้นครูจะให้เวลา1 นาทีให้เพื่อนสอนจริงๆซีเรียสนี่แล้วเมื่อไหร่ก็ตามที่ไม่ทันน่ะที่หลายคนรู้สึกว่ามันไม่ทันให้ยกมือแล้วครูจะหยุดให้โอเคป่ะคุยเลยถามเพื่อนเลยตรงนี้มันไปเร็วมากเลยอ่ะbreak for 1 minuteเอาไหมลูกใครเอามั่ง
ใช่อันนี้มันดูว่าอันนี้บอกอันนี้คนเลยทางเลนบอกคนหาคนนี่บอกคนวาวไม่ใช่ต่อมาเป็นคอมมอนถ้าเป็นคอมมอนโพลิเมอร์มันเป็นวาวแล้วก็แต่ไม่เป็นคอมมอนเศษว่ามีของอันนี้แล้วเส้นเนี่ยแล้วเราโวยนะแล้วเป็นวันละไหนเพราะคือย้อนกลับไปของมันจะเนี่ยมันก็การมันลงไปในวาวให้เราเองไม่มีอะไรให้เราทำเฉยๆต่อยังไงบ้างก็นี่เหมือนไอ้ยี่ห้อมันกลัวเราสอนดีแล้วเขาคนเดียวจะแข่งเรื่องนี้อันนี้ไม่พอจะกลับไปที่จะมีโมโมเลยนะโมโมใส่การโมโมใช้โมโมเสียโมโมซุนใช้การโมโมไอเดียที่ว่าไปสัตว์เยี่ยมดีดวนโมโมนี่กับเย็นนะครับเมื่อที่เหมือนกันคือรู้มันโมโมใส่ชื่อ
ไม่เอามาไม่ดีนี่นะมือก็ต้องวางไว้ตรงนี้สิเอาไหมลูกเอาเลยนะเดี๋ยวจะเริ่มต่อละอร่อยใช่ไหมตื่นเลยอ่ะไม่ตื่นเหรอ แกเอาน้ำก่อนกินแล้วก็กินแล้วจะน้ำเปล่าเลยเอาน้ำเปล่าเอาน้ำเปล่า
ไม่น้องหมดแล้วนะมันเลี้ยงหัวอาการมันเลยคุณไม่ควรนะคุณไม่ควร
แล้วทีเอาเริ่มนะช่วงนั้นเร็วรีบ
เราเพื่อนก่อนเราเพื่อน
ได้แท้
เราเล่นก่อนอยู่ต้องรีบเลือกเอายืมไม่รู้นะไอ้สัตว์
เป็นไงดีไหม
ขึ้นจมูกจ้า
ไม่ใช่ไงถึงได้บอกต้องกินน้ำก่อน
สัตว์ในท้าย
บอกแล้ว
แล้วไหนมาแล้วก่อนไปเอ้าไอ้เหี้ยกูไม่กล้าหายใจอาจารย์เลยหายเรื่อยๆไม่เคยหาย
Okay, sit down, please. Okay, now. Alright, so next, let's talk about like the categories, alright, of polymer according to the property and according to the structure and property. We divided them into what? Into thermoplastic, thermoset, and elastomer. So have you heard of the word that plastic can be recycled? You think all of the plastic? Do you think all of the polymer can be recycled? No. Why? What is recycled? That exactly. So reusable. That means what you have is you use this polymer, and then later on you melt it. And when after melting it, it can be reformed into another kind of polymer. You see, not another kind, another shape of polymer. You see that? Okay. Let me ask you. We have three of them. First is thermoplastic. Second is thermoset. Third is elastomer. If I'm telling you that only one of them can be recycled, which one will be? Why thermoplastic? Because it can be able to reheat. Why? Let's take a look right here. Okay? So in this case, what's happening is, if you have thermoplastic, it can be, right? Here is linear. And here is branch. Okay? So, how about for thermoset? So thermoset can be linear and it can be branch. But what's different between thermoplastic and thermoset is you can see the cross-link right here. You see that? So what does it mean? When we have cross-link and cross-link right here is covalent. So what do you think? Is it affecting the property?
No.
Yes or no? Yes.
Yes.
What property does it change? A lot of property. At least it's stronger. So that means when it has stronger bonding, you see that? That means it can be melt easily or not easily?
No.
Not easily. So you see that? So let's talk about this. Okay, imagine you have polymer, okay? You have polymer in solid state at maybe room temperature. And then you heat it a little bit. You heat it, okay? Polymer get melt. And then if you just keep heating and heating it, what's gonna happen? Polymer burn and becomes char, become carbon. You see that? Okay, so one polymer, this my level, my hand is the range of temperature. Okay, so what happened is, right? Melting temperature. Okay, so if like the temperature is higher than melting temperature, become melt, and then higher, even higher, it can be decomposed into carbon. Okay, this is one kind of polymer. Okay, if this polymer is another polymer, we have high melting temperature, and it's very close to the temperature where it becomes a carbon. What's gonna happen?
it can be hard for us to melt it and reform it because sometimes we just heat it and then it already become the carbon. You see that? So what are the cases on this and what are the cases like this? The one with lower melting temperature tends to be thermoplastic. And then like for the one with high melting temperature that can be so hard to reform it is what? Thermoset. You see that? And why thermoset has higher melting temperature? It has what? Bond cross-link. It's stronger and it's hard to melt. Alright? So next is what? Have you seen elastomer before? Have you seen structure of elastomer before? No? Are you sure? Are you sure? I told you, right? That this kind of cross-link with the link, with that use the chain as a linkage, right? We see a lot in elastomer. See? So, and these are covalently bond, covalently bond, covalently bond, covalent, and covalent. Okay? Right? That is the process. First, there may be the normal chain, but there must be certain process to induce this cross-link. Okay? The process to induce this cross-link is called vulcanization. Okay? So this is chain, this is another chain, and this is cross-link. You see? Covalent chain. Right? And commonly, people use sulfur to cross-link between the chain right here. Okay? One more time. Thermoplastic. You don't see cross-link. Low melting temperature, easier to recycle. For thermoset, some cross-link, alright? And it has stronger and high melting temperature. We normally don't recycle it. And then for the rubber or elastomer, we have cross-link in the chain as a chain, and the process to introduce that chain cross-link, we call it vulcanization. See that? So normally for the rubber, we don't do the recycle. You see, because pretty much there are lots of covalents. You see, it's quite strong. It's hard for it to be molten and then come back to use it. All right. Next. Okay, this and this. Which one is plastic and thermoplastic and which one is elastomer? Which one? One is thermoplastic, another one is elastomer. Which one is thermoplastic, left or right? Why? Because you see it right here. But if you don't see it right here, what's happening is you can see it from the cross-link. You see that? Right? So if you see this kind of cross-link, you can guess that it is elastomer. See? So what's happening is like I have thermoplastic and I have elastomer, and I try to stretch it. If my force is not too high, what's happening is when I release the stretching, what's happening? Elastomer come back to its original shape. See that? Why the thermoplastic? It may change the shape forever. You see that? Okay. So this is some kind of the difference between thermoplastic and elastomer. You know what? How many pages do we have left for this? 1, 2, and 3. Okay. What happened is right here. Okay, I told other sect that there was a wicked lady who asked this question in the exam. Okay, the question is, consider the following materials. Which one can be recycled? The polypropylene,
polyvinyl chloride, epoxy, silicone. Okay, A is epoxy, B silicone, whatever. And then choice number 1 is A and B. Choice number 2 is B and C. Choice number 3 is C and D or whatever. You see that? So that means you need to know everything correct, right? So what will you start from? First, you need to know which one can be recycled, right? Like if it is plastic, thermoplastic, thermoset, or elastomer. But right now, do you know which one can be recycled? Yes, it is thermoplastic. Next step, you need to know which one is thermoplastic. You see, that sucks. Alright? But, and I'm telling you that Wicked Lady, actually it was me who have like that exam before. Alright? So, what's happening is like, now you need to know which, when I talk about polymer, you need like polystyrene, poly whatever, you need to know if it is thermoplastic, thermoset, or elastomer. You see that? And this is the table showing thermoplastic. This is the table showing thermoset. This is the table showing elastomer. You hate me so much for having that kind of question. What do you think? Can you memorize all of them? I give you 15 seconds to complain.
Complain. Keep complaining.
Stop complaining. Stop complaining. It's already 15 seconds. Look up. You don't need to. You should memorize it, but I don't want you to memorize it because you're gonna forget anyway. We have the trick to guess. Okay? We have the trick to guess. Okay, so the trick like that. Okay? Which one do you think is the most common polymer? Thermoplastic, thermoset, or elastomer? Which one that you see quite a lot? What do you think? Thermoplastic. So you know what? Something that sound familiar with you. Like you can guess that it is thermoplastic. Right? So let's see about that. Let's start with this. Like PE. Familiar with it? Yes. We talk about PE a lot. Remember, PE is polyethylene is thermoplastic. Common polyethylene is thermoplastic. Alright? So how about PVC? PVC is it common to you, PVC? Yes. And the structure is like PE. You see that? PE is what? Polyethylene. Ethylene is C2H4. And PVC is what? C2H3 and 1Cl. You see that? PVC is thermoplastic. How about polypropylene? Plastic. You see? You have heard of it's so similar to ethylene. You see that? And then how about the polystyrene? Styrofoam, thermoplastic. How about here? How about like polyphenol? Don't worry about it. It's just like it can be used to make the fiber. That's fine. In case if they come out, that's fine. But like for PMMA, you don't know PMMA, but do you know acrylic? Yes. Thermoplastic. How about here? Polychlorotrifluoroethylene. Look at the word. Ethylene. And then chlorotrifluoro, that means what? 1 chlorine and then 3 fluorine. That will look like ethylene. Anything that look like ethylene should be thermoplastic. And that should be like, you can guess that it's some kind of like thermoplastic. What else? Teflon. What is Teflon? Replace all the H with F. You see, Teflon is thermoplastic.
all right? And then like, what is it? Like polyamide, do you know polyamide? No. You know nylon? Yes, it is thermoplastic. You see that? Have you seen polyester? Yes. And then like, polycarbonate? Polycarbonate can use to make the roof, the plastic roof. Alright? Okay? So the trick is what? Trick is something that is quite common to you. And something that has the word some kind of ethylene should be. Like you can guess that it may be thermoplastic. Okay, one more time. Polypropylene? Yes. Polyethylene? Teflon? Nylon? Polycarbonate? PVC? You see that? You see? You don't need to memorize all of them. Just guess. Alright? You hate me a little bit less. Alright? Alright? A little bit less. So, how about here? Oh, by the way, one thing. Shh. Sometimes you see something up here in the list of thermoplastic, but sometimes some engineer just put these monomers together or polymers together and then they do the cross-link or something like that. So the same thing can appear as thermoplastic in case if they engineer it. They just introduce a cross-link or whatever. You see that? But if in case, if the exam comes out, it should be something like this common without doing anything else. You see that? Because like, some people may see like, oh, Teflon. I thought that Teflon was like thermoset. Okay, common, like original Teflon, it's just like thermoplastic, but they may do certain cross-link to become thermoset. You see? So that's why I told you that material is some kind of like open-minded subject. Alright? So next, thermoset. Phenylamine, like urethane. Have you heard of polyurethane? You may have heard of it, but you don't know what it is. Here, who has roommates? You don't, right? But like, has roommates who snore so hard? If roommates snore so hard, what do? You just kill them. No, not really. What you need to do is to buy the earplug. Earplug is some kind of like soft foam. Those are polyurethane. And urethane can be used to make the seats of your car, right? And urethane is thermoset, right? So what else can be thermoset? Epoxy. Epoxy, what is it? It's glue. You see that? Glue is thermoset, all right? And here, silicone. กระชูพีชีพในหน้ามองหน้าครู Take a look at my face. Actually, take a look at me, but especially my face. If I die, okay, they burn me. What's happening is they will see silicone. Alright? Alright? So what's happened is just look up. Okay, actually it's my nose with the silicone. Alright? Yeah, mom of her. My nose has silicone. Alright? So what's happened is what happened is so whenever I die, you should not take the silicone over there and make it to be the nose of yours, because silicone is right here is thermoset. It shouldn't be able to recycle. It cannot be reformed to another shape. You see that? Alright? Silicone. Silicone is like thermoset, and you know what? Certain kind of silicone can be engineered and make it elongated, and we get the elastomer. Okay, so some silicone can be just like elongated. If you take a look here, elongation in elastomer or rubber is like hundreds or 1,000%. But if you take a look at thermoset, you see elongation just less than 10%. You see that? ฟังนิดนึง
thermoset is quite strong. So that means you cannot stretch it that much. You see that, right? Okay, so that's pretty much. Okay, by the way, not pretty much. One last note, right here. Just want to give you the example of elastomer. Rubber sometimes end with isoprene, butadiene, something prene, diene, or whatever. Okay? Okay, ไหมคะ Everyone, give yourself a round of applause. We are done with the first chapter. And then we have, you see, okay? Pay attention. And you know what? Next chapter we have only 32 pages. I will try to go around half of the next chapter within 40 minutes. What do you think? You know what? If we can go to that, I told you, we go fast and we can finish the third chapter tomorrow. See that? And then like maybe even like the fourth chapter a little bit. And after we finish everything, what it means is that we have holiday. Like at the week before exam. Let's see, around 35 minutes. How many slides can we go? Okay? Alright. Everyone look up. Okay, in this case, this second chapter, we will talk about the what? Mechanical properties. Okay. แล้วเครื่องรอแป๊บนึงยังมีเวลาส่งอยู่ใช่ไหม Okay, I finish within 15 minutes, so you have some time. โอเคป่ะ ได้ไหม2 นาที เอ้ยไม่ใช่2 นาที 15 นาที จะได้มีเวลาอีกนิดนึง โอเคป่ะ 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 So class will over within 15 minutes. So pay attention. Right? Okay. ทันใช่ไหม15 นาทีทันน่ะทันทันเฮ้ยครูไม่รู้ไม่เห็นเดี๋ยวแกทำอะไรก็ไม่รู้นะแค่ครูรู้ว่าแกจะต้องทำอะไรบางอย่างโอเคป่ะครูไม่รู้ว่าแกทำอะไรแต่ว่าแกต้องทำอะไรบางอย่างโอเคป่ะ Okay, everyone look up. We have 15 minutes left and then let's see what we can go. Okay, so right now we are talking about the mechanical property of the material. Okay, so the issue that we are addressing is about concept about stress and strain. Okay, you are familiar with it. Stress is what? Stress is force over area. Strain is how long it is. Exactly. Stress is ความเข็นนะไม่ใช่ความเครียด Stress is ความเข็น Strain is ความเครียด Alright. So stress is force over area and strain is like the length, elongated length over its original length. And then like, let's talk about the second concept. Second concept is whenever we apply stress to material, there are quite a lot of time that the material change the shape. The change of the shape, we call it deformation. Alright? And then like there are two kinds of deformation. The first one is elastic, the second one is plastic. Okay. Guess this. If I told you that one of this, elastic or plastic, one of them, when we apply the force and when we release the force, it's gonna come back to its original shape. Which one is it? Elastic. You see that? You think about elastomer or rubber, right? So you stretch it and then you release it. It comes back to original shape. So what happens is deformation or change of the shape. If you have elastic deformation, that means if you stop applying the force, it comes back to original shape. Alright? But for the plastic, if you stretch it or apply force to it, apply stress to it, it will change the shape forever. It's permanent change of the shape. That's called plastic. Alright? And then after that, we talk about ductility. Ductility is the ability of the material to elongate. Alright?
And then resilient toughness, we're going to talk into detail a little bit. And the final part, we're going to talk about hardness. Alright, so this is something that we are going to talk about in this case. Alright, so when we talk about applying the stress or applying the force into it, how many modes are there? We can talk, when we pull it, we talk about the tension mode. If we press it, we talk about the compressive mode. If we just shear it, we have shear mode. Alright? Apply the force in like this type of direction, right? And then if it's just like how to say, just like torsion it, right? Bend it or whatever, right? We have torsion. Okay? So in this case, what's happened is go back to definition of stress and strain. Stress is force over area. What is the unit of stress? Newton per square meter square. And then what do we call it? In short, we call it Pascal. Right? Pascal is Newton per square meter. Right? And then like, have you heard of the word PSI?
Yeah.
PSI is what? Pound per square inch. It's also the what? The unit of stress. Okay? Alright? Pound ต่อตารางนิ้ว Pound per square inch. Alright? So how about the strain? Strain is delta L over L, right? What is delta L? The final length minus original length over original length. You see that? Okay. What is the unit of strain? No unit, right? Because it's cancelled out. Okay. I guess everyone understand this concept. What I can worry about you is just only this. Okay? Sometimes when we have exam, right? If there are some kind of long equations, they would have equations for you. Short equations, they don't. But even when we have long equations for you, they wouldn't tell you what symbol is what, right? So what you need to do is to know what symbol it is, what symbol it represents. For example, if you have stress is F over A, right? What is stress represented by? It is sigma. Alright? So in this case, alright? So we have here sigma, alright, is stress. And then like F over A. Alright? Okay? So let's talk about this. When we apply the force in the, what mode is this? What mode is this? I told you there are 4 modes, right? What are 4 modes? 4 modes. Right? First mode is tensile, then compression, what is, and then shear, and then torsion. In this case, what is it? Tensile. Because like the direction of the force is perpendicular to the area. You see that? So basically, like we have like, in this case, force over area. How about if we have the shear? The shear mode. What's happening is like the force may not be perpendicular to actually it's not going to be perpendicular to the area, right? So what do we need to do in case the force is like that? We just need to have the force into this direction. Okay? One more time. Tensile mode. Tensile mode. Force perpendicular to area. Okay? Shear mode. Force parallel, like has the direction parallel to the area. Okay? So for tensile mode, two. So tensile แรงตั้งฉากกับพื้นที่เชียร์แรงขนานกับพื้นที่ Alright, so tensile is represented by sigma. How about shear is represented by ทอบางคนอ่านเทาทอเทาเพื่อนอ่านเทา whatever. Alright, so okay, sigma. What is unit of sigma? What is the unit of sigma? Newton per square meter or Pascal. What is unit of power? The same. You see that? The same. Alright. So what's happened is in this picture, it's just to show you that one component may be subjected to all modes, like compressive, torsion, tensile, and like shear. See that? Just like these two pictures, just to show you that. Alright? So next we talk about the stress. Now we talk about strain. Shear stress represented by what symbol? One more time. Tau. ใช่ป่ะ Tensile stress. Sigma. Okay, so let's talk about the tensile strain. Tensile strain is represented by epsilon. Alright? So epsilon, what's happening is, okay, originally we have this black box, right? And then we pull it. If we use tensile mode, that means we pull it. What's going to happen? This box change the shape or not? Right? Yes. Right? So what happens is it becomes this green box, right? It's get longer. Why the width is thinner, right? The width is reduced. See that? So when we talk about the strain, we can talk in two aspects. The first one is how long it is, like how much longer it gets. Another one is how much thinner it gets. Alright? So for the how much longer it gets, we call it just like common strain. Alright? And basically it's represented by epsilon, which is equal to what? This, right? Extra length, right? In this case, extra length is represented by delta over 2. Delta over 2 plus delta over 2 is delta, right? Over original length. Okay? So, how about for how much, like how thin it gets, how thinner it gets. In this case, we call it like lateral strain. Alright? So for lateral strain, so we have epsilon of L, lateral strain. And then like, we get like how much? See, thinner it gets. Delta L over 2 and plus delta over 2 is like delta L. And then over, is it, right now, do we have it over length or over width? Over width. You see that? And if you notice, there would be some kind of minus, negative. You see? What does it mean by negative? Because it gets thinner. That's why it becomes negative. Okay, so let me summarize this for you. So when we have, like when we pull material, it can get longer and get thinner. Alright? How longer it is, we have epsilon equal delta over L. Alright? So how thinner it gets, we have lateral strain. And we think of it as epsilon L equal delta L alright, over the width. See that? So what is the unit of epsilon? No unit. Alright? Epsilon L, that's no unit. Alright? So next, okay, I talk about this part and I let you go. Alright? So that you have some time. Right? Here. Right now, what we are going to do is talking about the machine. Okay? We talk about the stress and strain. And that is one kind of machine that can give you the data of both stress and strain. So first, what's happening is you need to prepare your sample, right? So the way that to prepare your sample is a little bit not perfectly easy, but it's not too hard. But let's take a look at the way the machine look like. This is the machine. This is some kind of the stage, fixed stage, right? And this part can be moved, alright? And that is some kind of the grip, right? The hand to hold your sample. And that is another hand to hold your sample. So that's why you need to prepare your sample in certain shape. You see what? If you prepare your sample, it like long stress sample, very, very thin. So when you grip it,
right? When you grab it by the grip, it may be broken at the place where you grip it. See that?
So sometimes people need to prepare the sample into the dog bone shape. You see? The shape of dog bone. Just like to the grip, you can just like grip it easily too. Right? And basically, what happens is when you want to measure the stress, what do you do first? You measure the size right here because stress is force over area. So you need to measure the size so that like you know the area, cross-sectional area right here. And then you start the machine and they would start recording the force. And since you already know the area, so you know the stress. Okay? How about the strain? Right now, like there is some kind of strain gauge or extensometer. Right? First, they have like the gauge just right here. They know like how far it is, the space right is. And then as we just like start pulling, there's some kind of sensor to measure the length. Right? That gets longer. Alright? So what's happening is right. It's like that. See that? This is dog bone and this is the strain gauge. You see that? This is to make to do the measurement of polymer. You see? Polymer tube. Okay? So what's happening is we have after we get the result from that machine. What you can get is like some kind of like stress strain curve. Stress strain curve can be this shape, like this, or stress strain curve can be as simple as this. Okay, ba? One more time. Right now we talk about the machine. To measure the stress and strain curve, we call it UTM, Universal Testing Machine. What does it mean by universal? It can be used in several setups. It can be used to do the tensile. It can be used to do the compressive or some other. You see that? Alright? So, that's pretty much it for today.
Yay!
Tomorrow we meet at what? At 11. What room?